Today we are going to see 3 problems under the topic state space analysis. Coming to the 79th question, the electrical system shown in the figure converts input source current Is of t to output voltage V0 of t. The current IL of t in the inductor and voltage VCT across the capacitor is taken as the state variables, both assumed to be initially equal to 0. That is, IL of 0 is 0 and VC of 0 is 0. So, they are asking the system is whether they are controllable and observable. So, just first we have to find the state equation for the given circuit. Okay, this is a simple RLC circuit. For this one we have to find the state equation, then we are going to represent it, that is state space representation, from which we will be getting the matrices A, B, C. So from these matrices we can find by using the determinant. Okay, so if the determinant of QC is not equal to 0, then we can say the system is controllable. And also for observability, if we find the determinant of Q0 and if it is not equal to 0, then we can say the system is observable. So coming to the actual solution, so for this one we are going to apply the KCL. From this, Is of t is given by IL of t plus VL divided by R. So you will be getting the equation. So I am making the differentiation term to be there and bringing all other term to the right hand side. Similarly, the current across the capacitor, Is of t equal to IC of t plus VC of t divided by R, where R is 1 ohms. Again, I am making the all other terms except the differentiation term to the right side. So in this way I am getting the second equation. Given IL of t and VC of t are state variables, and also they have said Is of t is input current. I am just assuming Is of t equal to U, then x of t to be the state variables, right? So x of t is a vector, input vector, and x dot of t, which is the differentiation of the input vector, that is dIL of t by dt, and the second element is dVC of t by dt. And we know that the VC of t is output. So I am assuming y of t to be this C matrix into the state variables. The state variables, as I already told, IL of t, VC of t. From this I know the value for the C matrix, and coming to the actual representation. So this is the representation for the given system, from which I got the A matrix, B matrix. And for controllability, the matrix for the controllability QC equal to B, AB. The first element is B, second element is the product of A and B. For n equal to 2, because the order of A is 2, right? From this I am getting the matrix 1 minus 1, 1 minus 1. After finding the determinant, it is 0. So hence we can see the system is uncontrollable. And also we have to check for observability. So for that, C is 0, 1. The determinant Q0, that is the matrix Q0 for checking observability, is C transpose, and second element is A transpose into C transpose for n is equal to 2. Here also I am getting the determinant as 0, so hence it is unobservable. Hence the system is neither state controllable nor state observable. Coming to the 82nd question, a second order LTI system is described by the following state equations: d by dt x1 of t minus x2 of t equal to 0, d by dt x2 of t plus 2 x1 of t plus 3 x2 of t equal to r of t, where x1 of t and x2 of t are two state variables and r of t denotes the input. The output C of t is x1 of t. The system is, so they are asking to check whether the system is undamped or underdamped or critically damped or overdamped. So for this I am just getting the state equations and just bringing the differentiation term to the left hand side and all other terms to the right hand side. So in this way I am just arranging to get the state representation. And also we know that the output C of t is x1 of t. For this I am going to arrange in matrix form. That is, C of t is given by matrix 1 0 into x1 of t and x2 of t. Since x1 of t and x2 of t are the state variables, the transfer function is given by this formula, which is C into Si minus A whole inverse into B. So from the state representation we know what is matrix A, what is matrix B and what is matrix C. And by substituting and finding the inverse, you know that the inverse is nothing but the 1 by determinant into the edge of that matrix. And substituting and simplifying this, I will be getting the transfer function 1 by s square plus 3s plus 2. So on comparing the with the standard second order equation, I will be getting 2 psi omega n to be 3 and omega n square is equal to 2, which in turn omega n is root 2 radian per second. And from which I will be getting the damping ratio will be greater than 1 because it is 1.06. Hence we can say the system is overdamped. Coming to the 83rd question, the state transition phi of t of a system. They have given the state representation of the given system and they are asking to find the state transition. The formula for the state transition is we have to find the inverse Laplace transform of Si minus A whole inverse, where S is the simple, it is a complex matrix, it is a simple complex number and it is multiplied with the identity matrix I. So which is then subtracted from the A matrix, which I will be getting from the given state representation. And by substituting this one, I will be getting the matrix as 1 by s square 0 1 by s. And after finally we have to apply the inverse Laplace transform, from which I will be getting the for 1 by s the inverse Laplace transform is 1 and 1 by s square the inverse Laplace transform is t, and the second row 0 1. Hence solved. Thank you.